Please welcome Professor Joe Paradiso from the Media Arts and Sciences at MIT Media Lab for his keynote on sensing and connecting across scales. Joe has been here in this room, even on this podium, giving a keynote when computer science at this university was celebrating its anniversary. That was a very inspiring presentation, as are all these presentations that are coming from Joe. So he's directing the Responsive Environments group at MIT. He has a PhD in physics in Tufts University, believe it or not. He joined the Media Lab in '94, building up this group on responsive environments. He has also worked at the accelerator at ETH Zurich and CERN in Geneva. And he's very, how shall I say, firm in handling huge complex systems. And this does not end with physics. It even goes down to very simple humanistic things like music. So he is dedicated to sensing, sensor networks, and to mediate human experience with such systems, the interaction, the perception of it, wireless sensing, etc., ubiquitous pervasive computing, the Internet of Things. So all these topics that are in our call for papers, he has published a lot, and he is even a composer of electronic music, and this city has already heard about his compositions in previous arts festivals, so he's around from time to time, and he is very active in this computer music and unusual music topics aside his real profession. And this is what I want to give as a final remark here. He is not just a brilliant researcher. He is not just someone who is shaping the field in sensing systems and in all related domains of computer science, artificial intelligence, data intelligence, and you name it. I have had the experience, and this is why I have greatest respect to you, Joe, that aside him being a scientist, he is also a person who has deep respect against life in itself. And I think this is a feature that would deserve more place on this planet here, respecting individual life deeper, stronger, more extensively, the wealth of everyone who lives here on this planet. Please welcome Professor Joe Paradiso for his keynote.
Thank you very much for that wonderful introduction, Alois. It's been a real pleasure to know Alois for over 20 years now, the beginning of pervasive computing conferences that we used to have. I've known Alois for a long time, and I've always loved interacting with Jehu and his group. Linz for me is almost like a second home, in that I've been here so many times for events at the university, and also Ars Electronica, whereas Alois hinted, I've done a lot of work and many installations. At the Media Lab, we love to do certainly fundamental engineering, but also we like to use it in different ways, including art installations. So Linz has been a natural home for that. Anyway, I'm going to talk about very broadly sensing and connecting across scales, lots of examples that hopefully is relevant to the EWSN community, and I'll go pretty quick. This is my group. It's always important to credit the students who do the hard work, at the beginning of any talk. And I'm really fortunate to have an exceptional group of students come from all over the world, lots of backgrounds, lots of great engineers. Some of them are artists as well. And they just always inspire me to do the things that I do. So these are the people that did most of the hard work that you're going to be seeing here. As I mentioned in the title, I'm going to talk about sensing at scale. And I think if you want to take a look at one of the things that unifies what we do in the group, it's using embedded sensing, but doing it from the scale of wearables all the way up to buildings and landscapes, and now more and more space. So you'll see quite a few recent projects we're doing that are being launched or already out in space now. So I'm going to start with a little bit of a historical perspective. Alois hinted at some of this. I'll go pretty quick. This is a sensing conference. Most of you have done sensing for a while. I've been doing it ever since I can remember. That's when I won the science fair back in 1969 in middle school. So I built lots of different kinds of sensors and had lots of interactive demos before we could use computers for them. And of course, as Alois also mentioned, I love music. This is a primary driver in my life ever since I can remember, and I'm lucky at the Media Lab that I can combine some of that with the technical work. It's just a natural place to fuse both ends. Alois also mentioned that I did my PhD in high energy physics at MIT, and I really had the privilege then of living in Europe for 4 years, 2-year postdoc, 2-year doing my degree at CERN. But that is not CERN. Does anybody know where that is? That's in Hamburg. That's the DAISY E plus E minus collider. So that's when Petra was up. That was when Petra, just as we started, we had an experiment at Petra. My group had just won the Nobel Prize for work at Brookhaven, and we had a detector, a Petra detector at CERN. So I started it in Hamburg, but went to Geneva. And then I postdoced at Sister University here, a small technical college. Some of you probably know, ETH in Zurich. It was a fantastic time there. This is in the ETH Centrum, in the center of Zurich. Wonderful overview of the city. I did my work, unfortunately, in Hunkerberg, far out of the city, so we were more isolated, especially back then. But of course, it's a wonderful city to be based in. And it really grew my love of Europe during all that time. It's always great to be back. This is what I worked on then. It was a central tracker for L3. This is the LEP detector. It's the E plus E minus collider that's now in the tunnel where you have that used to be in the tunnel where we have the LHC now. That was our detector, the first precision detector with a muon system of this sort. The system was aligned within microns. This large chambers, that's a big magnet. You get these big flat detectors inside that have to be aligned to within microns. And I worked on that technology, but at that time I was working on the central tracker. So all the particles that come out of the collision, trying to track them. Of course, that is a sensor. In a way, it's a sensor network. Even the calorimeter back then was digital. We digitized right on the detector and sent the results out. That's common now, but that was the beginning of that kind of a thing. And then I left high energy physics. I kind of came back to it a few times. I'm still attached to it. It's a wonderful field. But I decided to do something else and get into spacecraft control. So I went to Draper Lab, the place that actually did the guidance and navigation for Apollo, back when it was the MIT Instrumentation Lab. And I learned all about how to control spacecraft. So I kind of left sensing, at least physically, working, I guess, more analytically, and developed control algorithms of all sorts for spacecraft of different kinds. And, you know, I thought when I left Draper eventually, I was done with spacecraft. That's not the case. We have a space initiative at the Media Lab. Students are very excited. We're at the dawn of a new space age. We're flying more and more things in space, including sensor networks now. And this is me getting karmically levitated on a zero-gravity flight. It helps a lot if you want levitation to have no gravity. So switching to music very quickly, this is me in Zurich, in my apartment. And the little bit of spare time I had from working on the detector, I was building synthesizer modules. I had a lot of ideas. I built my first synthesizers in undergrad. I kept on going, and it hasn't stopped. That was when I came back to the US. That was my apartment. So you can see my big modular synth around all the keyboards, which are fully integrated into it. I'm very much an engineer, so I love to build things. And this is here at Ars Electronica in the Bruckner House. The festival flew the whole thing over to celebrate its 25th anniversary, since synthesizers were a big part of it. You're hearing some of the music I made with a patch like this. I tend to put in these huge patches that make music by themselves, and it keeps on going. This is my basement Just a month ago, I did a large autonomous patch that I streamed into the Media Lab, streamed all over the world actually, but it's for a Media Lab event. And again, the complexity of all this patching, it's a connection, this network very much, gives you tremendous complexity in the sound and music it makes. So this is just something I made a few weeks ago. I modify all my pedals so I can put voltages and gates into them. And again, when I'm doing this is a Casio, an interface I made to a Casio so I can control it. These are things I built when I was an undergrad that I've expanded since. And everything is tightly interconnected. It's a very complicated system. Things come in and out. It's got a whole set of complicated rules, but I improvise them. I'm an engineer while I do it and a composer at the same time. It's a special state to be in. It can be exhausting at my age now, but man, I don't want to give it up. It's so much fun to continue doing this. There's a lot more. If you go to search for Paradiso Modular, it's the YouTube channel, or Paradiso Synthesizer, you'll find lots of things about it, more music. Anyway, that's a little bit about me. Let's get into sensing. I'm going to start with some stuff on wearables, do a lot of work with wearable sensing for years and years in my group. More and more wearables that look into your affective state. Some stuff on micro-robots, smart fabric of different sorts, putting sensor nets into materials, and then, if we can, virtual worlds and extensions of sensor information in VR environments. We're doing lots of this stuff, still are. Media Lab, some of you may know or remember, we kind of were the place where wearable computing, as we conceive of it now, was more or less born. This is in the mid-90s, and it was driven by our students, Thad Starner and Steve Mann. Some of you may even know or have heard about. They're at opposite ends of the picture in the upper left. They had their own distinctive visions of wearables, but they lived by what they preached. They wore a computer with a display, always on basically throughout the day at MIT. They would even be able to go to classes. They had special permission to go with their wearables back then. They were the harbinger of still what the field is yet to become, but what we can see starting to evolve. And they had lots of acolytes of all sorts, including faculty and students using their wearables. This is the first project I ever did in wearable sensing, because we hosted the world's first wearable computing conference at the lab. I figured I'd build a wireless embedded sensor system for a shoe. So that's a dancer shoe, had 16 sensors, measured lots of things. And you can see we're using it in real time, so as the dancer moves, the music gets changed. We have actually even performed this at Ars Electronica around 2000. Lots of evolution and development on this. This eventually led to some wearable gait analysis. And it's again what kicked it off. And Alois went to what's in a phone now. I would go through the 16 sensors in the shoe and people would laugh back then. But now we accept it. This is the world of embedded sensing. We went from there to do work for, again, gait analysis, but also I met the doctors for a sports team, little sports team in Boston called the Red Sox. Some of you, if you know baseball at all, would know about them. They were interested in trying to do wide range biomotion capture with IMUs, wireless IMUs for their players. This is in the mid-2000s that we did this work. And then you could just go out and put the sensors on a player at the bullpen or a practice, get data, and then evaluate them. So back then, there was no protocol to do it. There's no device to do it. I think we did the first wide-range sensor for sports. We even had analog devices modify their gyros for us so we could use them at 10,000 degrees per second and more. We had airbag accelerometers and low-G accelerometers fused together to get the full range of motion. And we needed to do our own wireless network to get the data back at a kilohertz full-state updates. There was nothing around that really could do it back then reliably, so we had to build our own. Different world now. That led to sensors to try to control energy in environments. This is a very low-power wearable activity tracker we did in the late 2000s. It would track personal environment. You could say if you're too hot or cold, and it would adjust the HVAC with an inferred comfort model. So you'd label the data, it would infer comfort, drive the HVAC with comfort. And we're starting to see that beginning to roll out with smart thermostats. They will soon fuse with wearables, just starting to happen. We were playing with that back then. This is another sensor that some of you may know, Google Glass, right? Sensors get to be packaged. Why not use the ones that are in things that you can just buy and wear? This is my student, Nan Zhao, came originally from the TH in Aachen, did her diploma with me and then her PhD. She is controlling lighting with glass. We did a lot of work in lighting control in the group. This is one of the ones that based on context. So the sensors in glass are looking at how much light's coming into Nan's eyes as she's moving around. It's adjusting the lighting dynamically. It's an agile Philips system that we had then that was unique at the time. So it's always getting the right kind of light no matter where she is. she's in a conversation, the sensors detect that she's talking, she's on the phone. We fade the room into something that's better for social interaction. So it's a warmer light. Again, the whole idea of a light switch was starting to be obsolete then. It is obsolete now. And why not drive it through context? And that's what we're doing. And eventually a colleague comes in and knows she's being social, and it gets into that mode. Instead of changing just lights, why not change the whole environment of rooms, right? Eventually we'll have smart wallpaper everywhere, so you can really start to play with imagery as well as lighting. Displays are getting big and ubiquitous. So we thought about trying to capture the gist of places, like a library, right? Can you bring that into the place where you work? And what kind of effect does that have on somebody? Can you measure that and then have the environment dynamically adjust to try to suit how you're reacting? So we did this project called Mediated Atmospheres, where we had a set of wearable sensors that measured the affective state of the user. Sorry. And we had lighting and audio and also projection that could change dynamically according to what we saw. So this is a proof of concept. Somebody has time on his hands. The sensors work, by the way. We got our features, and we could drive the displays and the output. We didn't do the closed loop yet. So it's just showing more or less what's happening. He's stressed out. He's got more work piled onto him, so he gets even more stressed. But then the room picks that up, and it gets into the mode that is suitable for him, which in this case is the woodland. So he gets relaxed. He starts to feel more restored. And now he feels more in control, starts to work. The room detects that too and goes into the library mode, which for him is great for flow. So that was the pieces were working. It wasn't closed loop. This is. So here's non-working. You can see the red dot here is the current state. The blue is where she wants to be. It's reweighting the effect of the images and bringing different ones up to try to bring her into a space that's focused and restorative. And eventually she gets close. She has gone on to make a portable version, working with Steelcase. We have a lot of industrial partners at the lab. We worked a lot with Steelcase. This is a version that also has a scent display, can make smells, can change the airflow, so on and so forth. And it's mobile, so you can move this anywhere and have your virtual desk in different physical environments, but it can virtually bring you places and again adjust to how you're reacting to it. We're fascinated to bring you to a creative place too. Creative places, there are different kinds of creative environments, but one that I'm fascinated with is clutter. I love to go to stock rooms to get ideas, and it's hard to find a stock room at MIT anymore. I tend to go to like a home goods store. You find all kinds of shelves with great things. But you look at designers and creative people. Ray Bradbury's a famous writer. He had all this stuff to get ideas from. Marvin Minsky, some of you may know Marvin. He's one of the pioneers of AI. I had the pleasure of being his colleague at the Media Lab for years. That was his house. And everywhere you look in Marvin's house, there's something really interesting. There's some idea of just that's speaking to you from that. So you can go into a cluttered environment, get an idea, and then go back into a laminar environment to try to develop it. So I think we're on the verge of being able to really bring ourselves places that are productive for us in different ways. And the room becomes partner. Instead of measuring with these old wired sensors that we had, why not try to measure with things that are less cumbersome? So my students developed this set of glasses they call Captivates. Just won some award at the Ubiquitous Computing Conference last month. Some of you may know about this platform. It measures, it has sensors, don't necessarily look out, they look in. They measure your internal state. So we've got thermopiles at the temples, also at the nose, look at the difference that can relate to cognitive load. We get a full eye on you to look at head tracking. We look at eye blink and eye dynamics in different ways with sensors, lots of other things, more detail here and what's on there. And we're adding also environmental sensors. We're actually looking at how the air quality and the environmental quality of the space you're in now can affect also your state. We're collaborating actually with people at the University of Freiburg now in a set of tests we're going to run with this. In addition to different groups all over the Media Lab. And it's got LEDs that can light up for alerts in different ways. We're actually looking a lot at the nature of what these alerts can do. But also we're looking at, they can light up the face. So for events, you can light the face up differently, and we can track them. If you have an indoor VR tracker, you can actually track these glasses very accurately. It's using the HTC protocol. My students actually spent time in Shenzhen. We had a class at the Media Lab where you would learn about manufacturing, so the students would go to Shenzhen to do that, and they learned all about how to embed technology into glasses. And they've done a nice job. We have an eyeglass manufacturer actually at the lab that they worked with as well. So we've turned out a bunch of these that really are beautifully embedded. And the data is looking good. This is looking at eye dynamics, eye blink, things like that from one of the glasses. This is looking at a bunch of the sensing, including the thermopiles. We're getting some indication that we can begin to back out something like cognitive load from them. We need more work, but all of it is useful when you fuse it together. David Ramsey, one of the architects of the glasses, got to be fascinated with attention, and you can barely see this. This is his introduction slide. He's very much interested in the quality of experience. Can you actually start to measure and infer that with sensors like the glasses and other things that he's building? How can we determine that people are engaged and at what level they're engaged with something in? So he's done a whole series of design probes for this. This is a watch that he built, and my students have built a lot of watches. And nowadays I ask them, do you really want to build a watch? There's so many open source watches, you can now hack it, get a watch, do what you want on it. He built a watch that doesn't tell you the time until you guess it. And that's kind of hard to come by now. So it's got a rotary capacitive sensor. You have to guess the time and it'll tell you the time. He's doing this to look at how people's perception of time changes when they're engaged in different tasks. It's got lots of other sensors on it. This is a breakdown. Some of you built hardware. And indeed, you can see effects, depending on how engaged they are. Their perception of time can vary widely. We've known this anecdotally. People have measured it different ways. This is a very elegant way of doing it. Instead of interrupting the person, they want to find out what time it is. They can try to guess it first. This is another device that he built. It actually pokes the leg, which is a little strange, but he's doing it to see at what level will you be aware that the thing is poking you. And if you're more engaged, you're going to be less sensitive to something like this. And he's got data that basically indicates this is the case. It just ramps up. And then when you detect it, you push a button on your phone or device. It'll reset. And it looks at how long it can go. We've done a lot of work in my group with audio. We're probably starting to do a lot more with it now, too. It's fascinating what you can do with audio and sound now. And my student Ashwarya was working with machine learning models to try to get audio sensors to listen and hear the way people do, to react the way people do, not just a spectral feature or something that's machine learned for only one thing. Try to get it to pay attention to sounds that the humans would. So this is her telling you a little bit about it.
When we form memories, not everything that we perceive is noticed. Not everything we notice is remembered. Humans are excellent at filtering and retaining only the most important parts of their existence. What if our technology had the same ability? We've run thousands of memory tests to understand how easily different sounds are remembered or forgotten. With these results, we've built models that use either low-level features of how something sounds or high-level features about what made that sound in the first place to predict whether you'll remember it.
These models work well on our test data, and we are actively building them into real-time streaming prototypes. This technology will enable portable devices that can compress audio storage by capturing only the sounds that matter the most, assistive devices that store only the things you'll forget, devices that capture the essence of an auditory environment, and wearables that can manipulate the sounds you hear to make them more or less memorable to you.
So we've rolled out a bunch of different tests. This is one of them where she trained her network to pull out different kinds of sounds that are relevant using its model. She uses mechanical Turk. She has people rate sounds in different ways, and then she can twist them into different kinds of frameworks when it's playing it back. So you can compress your whole day, a little bit like Microsoft SenseCam. Some of you remember that, compresses your whole day with visuals. Now we can do it with audio. So what does a summary of my day sound like if I wanted to, say, emphasize more music or speech? And we all wore them for weeks. This is just a short summary. I'll only play a second of this. This is more musical emphasis.
Is the first inauguration in the history.
I was playing my synthesizer a lot during quarantine. I was listening to a lot of Indian music actually at that time. So you're hearing little bits of that. So you're hearing other things, but it's really kind of a musical summary of my day. This is one emphasizing speech and more valent speech, actually.
Like a crazy person.
Yeah. But I mean, that's
Want to?
a lot of frustrated Zoom meetings. Switch. You got to switch to different. I don't see any of that because, look, it's a pepperoni pizza. And I'll have Mayan is liberal. For lunch? No, for dinner we're going to have... What? Different ways to reflect on your day just by tilting the way you interpret the data in different manners. And at some point we'll all be wearing microphones, or already are to some extent. I certainly am now. But can we start using this data to reflect on our life, on our experience in different ways? Then what about a wearable that's dynamic? So my student Artem, together with Cindy Cowan and Sean Fulmer at Stanford, one of our alums, built these things we call rovables. So here's a wearable that decides to go where it should be to do best what it wants to do. So here they're going down your sleeve, and that's for motion capture. They have IMUs on them. Here's a display going to where it wants to pretend to be a watch. It needs more area in the display, so it finds a neighbor, so it can assemble. This is some sort of notification or something they do. This is Cindy Cowan's work. It's a microphone, a piece of jewelry, but it's a microphone. It goes to where it should go when you get a call. And of course, Arkham did a lot of work with navigating on clothing and stuff like that in his papers and pieces. But I pushed him to go a little further for his PhD and look at robots that crawl on the body. And crawling on the clothes, you can think of things that you can do, but it's still boutique. But if you can crawl on the body, you can think about it being a medical platform. So you can do different kinds of diagnostics if you carry a camera, which we did up on top. You can give microtherapies. Maybe you can test the skin in different ways. And you can go further and do more things as the technology gets better. We actually got to the point where it didn't need a tether, and even the pumps get smaller. So this gets more and more feasible to be a standalone operation. Tattoos and skin features have been used in dead reckoning to figure out where it was as it moved. This is a durometer. He turned, for his thesis, he made a bunch of compliance measurements of the skin. It would just march to different points, measure how your skin was responding, and then we all had graphs of what our skin was like. It made the cover of IEEE EMB. This is the main journal for electromechanical stuff in the IEEE. They like the novelty, I think. Okay, why not go and put these on other things? We did it on humans. Let's do them on spacecraft. And Arya Lekbla, who did her PhD in my group, runs the space initiative at the lab now, is fascinated with the idea of little micro robots crawling outside of spacecraft to do diagnostics, to look for micro cracks, to look for structural fatigue, to look for things that are going wrong and explore and do diagnostics. So we built a fleet of them with sensors on them that are relevant for that. We had acoustic probes, we had thermal probes, different kinds of cameras, things like that. We ran them on zero-gravity flights to see how well different kinds of locomotion models with sticking to the different substrates would work. And they all seem to work fine. But we're going to the moon with it. So this is a Lunar Outpost. It's a rover that is launching to the moon next year. Nokia will be the main payload. There's going to be a 5G network on the moon. I don't know what its client will be, but it'll be a base station. And we have space on it to run probably the world's smallest planetary rover. So that's a little micro rover. It's going to crawl out on top of the main rover. That's also its thermal maintenance system, its radiator. So we're going to measure the thermal response there. So we have a bunch of sensors in there to do it. That's the actual rover that's going. It's evolving a little bit, but it's going to be delivered imminently now. It's going to crawl out of a little garage we're making on the top. And at this point, it has a thermal pile to measure the thermal parameters. We're going to put thermal cameras and other things on it, but every gram counts. At this point, we're really doing it as a proof of concept where it can crawl out and be controlled and navigate. It'll have a wireless link to the rover. The rover then, on the other hand, goes back to a base station here. We're also fascinated, as I mentioned, with how sensor networks and the things that we talked about as being sensor networks diffuse into media, into materials. This is stuff that I started talking about in the mid-2000s, and we've had a bunch of projects in the group that have looked at this. We have sensors and processing in a local area, and then you've got networks that connect them, so it's ideally scalable. Start with push-pin computing. I think we presented some work on this at EWSN, actually, back in the beginning of the 2000s. Lots of distributed computing platforms that are wired or tiled together. We started putting them on flexible substrates and now fabrics. I'll talk about just a few at the end here. This is the sensor tape. So this is a sensor network on a tape. It was inspired by sensors as commodity, right? We're starting to see ourselves being at the edge of that. Can you look at something like a roll of tape that's a sensor? It forms a network down the line of the tape. You cut it where you want. You're seeing it in LEDs now. This is before you get the LED strips. And hook up to the end and it configures. So this is our WISP paper. That's the sensor tape with its inspiration. We had IMUs going all the way down, so you could get basic geometry just from the gravity of the IMU and the gyro. We also had time of flight sensors, so we could actually look at proximity. And again, you can cut it, you can join it, just like regular tape, and capture the geometry of things. And Artem was doing so much CAD in those days, he had back problems. So why not measure his posture? This is moving on now with work that Ermedi Wixono is doing in my group. He came to me actually from Trosser's group at ETH and already knew a little bit about smart fabric, but it totally exploded once he came to my group. He's looking at incorporating fairly sophisticated processing and sensing in networks right into fabric with flexible connectors. We're actually even doing a proposal now with Joel Fink's group at MIT, the Fibers at MIT group, where we're putting computational structures into fibers. Actually, Prabal Dutta is one of our collaborators. He's here. I don't know if he's physically here now, but he's coming to EWSN. But it's exciting to think of sensor nets actually on fibers that you can actually begin to weave and knit and put into looms. So it's going to go a lot further. But Ermedi has been looking at these kinds of ideas. Again, you can just cut it as you want. Ideally, it'll self-configure. You've got a sensate, flexible, stretchable network that you can wear or put on something. My group wrote all about this in a recent issue of IEEE Pervasive Computing. Some of you may have seen it. If you want to get more info in more detail, I'll show you a bit here. There's more there. Ermedi's work began with this vest where he had lots of sensors to measure lots of biophysical parameters, very, very dense sampling across the shirt, and again, using serpentine connections, lots of embedded sensors and stuff. It didn't really form a network. It was more centralized around the edge. But this is where it all started. And then he developed this, which is a network. It's kind of a framework for a garment, just a very early version. Lots of sensors and flexible interconnects, stretchable interconnects between them. And it measures lots of things, and some examples of that. He's also making weaves where the weave itself can tell you pressure stretch and stuff. This has been around in the community, certainly since the late 90s, early 2000s. We did work in the Media Lab, but in the EU, there's been some great work, the Wealthy program and others that have explored this. But the fabrics and the materials get so much better now. You really can get reliable strain, stretch, and pressure coming from fabric now. It starts to be very usable. So Ermedi has been doing all different kinds of weaves and different kinds of resistant materials with pressure, piezo-resistant materials, so on and so forth. So he stitches it out and make whatever pattern you want. It can be functional and aesthetic at the same time. We got this huge knitting machine in my lab where fabrics just get extruded from, sensate fabrics. This is one that I actually could use. My sloppy psychedelic keyboard playing. He made a fabric keyboard that you could roll up like a scarf. It would measure actually pressure, but you could really play it. And it had electrochromic threads. You could change color. So you just, apply a little current to parts of it. You can make different parts of the keyboard change its color if you want to change indications of playing style. There. But he went much further. This is the final keyboard that he did. And it measured capacitive non-contact all the way across. So you know where you are, you know how far up and down you are before you even touch it. And then once you touch it, you've got pressure sensing and you can play it. That's just a regular diatonic keyboard. And I don't know any keyboard that will stretch. This one measures stretch as well. We have students that play much better than I do, so it's always great to have them around for a demo. Jordan Rudess, some of you may know, I'm a huge prog rock fan, some of you probably follow the genre. Jordan Rudess is one of the #1 keyboard players in the world. He's a keyboard player for Dream Theater. He is excited about this. He's been bugging us to come and play it. And within about a month, we're going to have Jordan over to give it a try. So that we're all looking forward to that. Ermidy's also been doing what he calls 3D knits, where he can knit with a thread that, or a yarn that has wax embedded in it, and you can basically melt the wax a little bit and form it into a semi-rigid surface. So he's been knitting these socks that are kind of quasi-shoes and all these other things, and also knitting garments you can put around your arm to measure blood flow, so on and so forth, with fine grain. So he's got pressure sensors, row column matrices in these, where you get really good resolution coming from them. It got on the cover of the MIT homepage after our EMB paper. This is just the pressure map of one of his socks with a wireless interface from his foot. So you can see the fine grain he's got in this. We've also made carpets of various sorts too, with electrosticker material in between, so when the dancer's on the carpet, you can measure pressure and location as the dancer moves. This is won the Lexus Design Award, and won the South by Southwest Innovation Award, and it's just won some other award recently too. Ermidy's been doing very well with these things. This is a dancer on it. This is a mapping that's done by one of my other students who's a good musician. So as she moves around, the sound evolves. It's kind of new agey. But again, it's evocative about what she's doing, all going through the carpet. We've done lots of other pressure sensing floors in my group over the years, but this is probably the most elegant one we've ever done, and very, very usable. This is Ermidy's sock. He's been doing machine learning on it, so he can recognize steps, going into the Minecraft version of MIT. He can do yoga poses, and it recognizes them all through the pressure distribution. This is another project we're doing in smart textiles. This one is actually flying on the International Space Station as we speak for the second time. It flew as a passive sample outside the Japanese module, and now we have an active sample that's flying and starting to collect data now. It is a piece of beta cloth, which is the cloth you wrap spacecraft in. It's that white cloth. It's meant to be a thermal protection as well as protect against micrometeorites. But there's a real interest in trying to gauge the quantity and type of micrometeorite environment that you have. And if you can put little piezo fibers into beta cloth, you can start to measure that. And Juliana has done that for her PhD, and that's essentially what's flying out there now. This is the passive sample that flew on the space station. Everything came back. Most of the fibers actually survived perfectly. So we learned a little bit, but it seems like this is going to be able to work in these materials. The fibers are still active when you get them back in the lab. This is a flight version that she's prepared here that's up there now. This is using a fiber developed by Joel Fink, our colleague at the Fibers and MIT group. We put several of those in there too. He's essentially a thread that that he pulls. He just extrudes it, and it's got piezo elements. She's gone to all kinds of impact facilities to measure how it performs, to characterize how these things work. So you shoot little microparticles into it and look at the response. And this is essentially what's flying in the space station now. So it's got the sensor out in the front, it's got some electronics in the back, it's got some calibration to be able to launch acoustic impulses into the fabric to measure how the sample may be changing over time. And ideally, we'll be able to hopefully get evidence of some strikes. That's it launching, and it's deployed. And she's fascinated with cosmic dust. She wants to build a cosmic dust detector because we're all made of supernova dust. There's still some of it out there. You start to find it at the source, at least out in space before it comes down. And that's another thing she aspires to do with this kind of technology. Bit of a stretch, but she's excited about it. It won actually just now in the NASA Tech Briefs innovation contest we just heard a few days ago. It won in aerospace and defense the top prize. But also the grand prize of the whole contest is another one of my students, Ali, for Flow.io. It's a DIY open source pneumatics toolkit. Some of you may have heard about it. I'm not talking about here because it's not really a sensor, but the group's getting a lot of recognition for this stuff. So my last part of the talk, we love to be with people. And as Alois mentioned, it doesn't have, it's great to have it happen again. It hasn't happened in a while. This is the Linzer Kleinwoche, the big festival on the river. I've been to probably 5 or 6 of them over the years. It's always fun to be there, to see this huge spectacle that goes on in the Danube, but to be with all these people is really exciting. I love concerts, as you know. This is the concert I went to before pandemic. I had to give a talk at Imperial College, and I made sure they timed it when my favorite band, Hawkwind, was playing. So this is the Roundhouse, beautiful venue in London. And it was great to see the band there. But yeah, the press of people is so crucial. I mean, this is what we had during pandemic. This is a prog rock festival I attended virtually. It's a band in France. I've got a nice TV in my living room. I've got great sound. I even have my pet rabbit, Otto, at the time to keep me company. But it's not the same, right? How can we begin to play with the idea of presence so you really can start to be places? And we have sensors all over the place. Can we start to play with the idea of sensing to do this? This is what we had during pandemic. At the beginning of Zoom meetings, my group, no one knew how to handle it. No one was too happy. We got used to it, but yeah, it's not as good as it can be. So how can you leverage these sensors and start to connect to different spaces in different ways? Well, I've written about it a bit. Some of you may have seen it. Scientific American ran an article that my student Ferscha and I wrote in 2014 about extending presence through connecting to sensors. And this is an example. That's the Media Lab, beautiful glass building. Some of you have been there. It's our new building. It was 10 years ago now. If you look inside with a special view, you can start to see the sensors. So we built this thing we called Doppel Lab. And this is an example. So we're making the walls translucent. We're showing all the HVAC sensors in the building with these virtual representations. If it's blue, it's cold. If it's red, it's hot. The flashing circles indicated that you're at a set point, essentially. That was temperature meeting in the atrium. We had sensors there. This is the actual building. You see people walking around if they have RFID. We have readers at all the main areas. Again, you can turn the walls off and look through the building. Even if people tweeted, if they tweeted near, it would show up near their office. So tweeting is kind of a virtual sensor we play with. You have microphones, and you can hear people talking if you got near the microphone in the virtual world. But you can't understand a word. They're speaking English. We actually obfuscate the audio right at the sensor. And this is 2012, 2010 when we did this work, before really anyone that I know about called this digital twin. Now, of course, it's the rage. We used to call it cross reality. We had to make up names for it. It's a big meeting when lots of people are at the lab. This is a day passing in seconds. So the building's in setbacks, so it's not regulating well. It regulates and the atrium dries up. People show up. Then we went outdoors. So, what if you put the sensors in a beautiful outdoor environment? How do you connect those to people? And one of my colleagues going around at Davenport co-owns a large cranberry farm. It's about, 600 acres that she was giving to a conservation society, turning back to nature. So we figured, okay, let's put sensors on this and capture the whole essence of this transition. So we built a little sensor node that was an environmental workhorse. It had a set of basic sensors in it, but since it was a wetland, we could plug lots of sensors in, and in this case, we had a lot of sensors in the ground to measure soil properties, hydration, pH, so on and so forth, soil temperature. And we had a solar cell on the top with a little bit of sunlight. It would power this thing for a while. We built 200 of them. We put them all over, so different kinds of terrain. This is a transect. This is a line going across. Sensors in the ground, we got really good at doing that and calibrating where they are before we started the sensor. We had a wireless network to tie all our areas together with directional Wi-Fi. Then we had a wired connection at the head end. This is a deployment map we made. Everything is all interactive. So you can go to one of the sensors. That's in the transect. If you click on it, you can see the sensor values and see a picture of the sensor when it's deployed. If you go back to another one, again, you can see the students deploying the sensor. That's Nicole and Spencer, and you can see the data. So the whole process was all systematic. Just with your phone, you locate it. It's just a GPS, boom, you got it. You take a picture, you're done. No power in lots of these areas, so we just use solar cells to power our base stations. Where we had a base station, we put in a camera as well. And lots of YouTube wildlife stars there now, especially the heron. People love him. But again, you put a camera in the wild, you pick up lots of things, and indeed we did. Lots more there. And again, we got data. This is temperature over the course of a year from different parts of the property. We did a lot of work with hydration. Part of Brian's thesis is working with soil scientists analyzing hydration. So you're seeing effects of day-night diurnal shifts, storms, rainfall penetration, different parts of the property, stuff like that. But we ran it to a virtual world. This is the exciting part. Why not do the same thing we did with Doppelad, but do it outdoors? So we had a virtual tidmarsh. We had the whole area scanned. We would populate the flora and the fauna with things that were like it there. We had machine vision running on cameras and would grow the right kind of plants. If it rained virtually, so on and so forth. You see it in Animal Crossing now, but we did this back 8 years ago. You can look at different lenses. Every time you see a bubble, the sensor is updating. This is, you can see the values. You know, the music is coming from the sensor data as well. As you move around, depending on temperature, humidity, and soil parameters, it changes. The animals feed on the sensor data, so as the sensor data changes, they change. This is another composition, much more spatialized, done by MIT composer Evan Zaporan with us. So again, through the eyes of a composer, or ears of a composer, you can start to visit these places and experience them in ways you never could with the sensor data driving it all. And of course, the animals, we could drive them with the sensor data, and depending on the history of the sensor value, they could change. This is started as a deer model, but Dawn, the student who did it, who's an artist, he made it kind of like a ghost, and depending on what the sensor values were integrated over time, the animals would be very different. So you really can play with different ways the data appears in these environments. And we have microphones all over the place. So if you have all these mics, what can you do? You can start identifying different kinds of bird species and wildlife. We can localize it, have it identify in real time. Look at species coming in and out during the day. This is actually before eBird had taken off. This is many years ago. And you can look at different bird species coming in. In the morning, you've got some, then in the afternoon, and it's quiet in midday. You can see different Canada goose coming in different years at different times. Cicadas, different broods hatching. This is a big year. But then, can you start to localize it? One thing I really like to do is have all these microphones bring the real world sound into the virtual world from the place where you are. You can't just sum the microphones because they have different delays to different sources. You hear an echo. Can you actually isolate foreground sounds, drop them off, blend the background, and put the foreground sound back in the right place? So my student Spencer essentially did that for his PhD. With all the microphones, you can locate them with some processing and time-of-flight localization. You can actually identify a foreground sound and then locate where it is. And then here, he dropped it into the virtual world. So here's just summing the signal. And it's kind of like an echoey sound, and the right-left is not exactly where it should be. But if you separate it out, well, I mean, it sounds much better. So no echo, and you can't really hear stereo so much here, but it pans right-left much, much better. So again, you can just take a real environment, abstract it to background and foreground, and then bring it back into the virtual world exactly like it should be from where you are virtually. And what if you're physically there? I'm close to the end here now. Can you start to tunnel into the sensors through a wearable and enhance the experience of being there? I think this is one of the exciting futures of augmented reality, enhancing the real presence. So we built this device with bone conduction headphones. We don't want to cover the ears. And we had all these sensors to try to gauge attention. The idea is if you're paying attention to something, fade up the sounds from where you're looking. But this was all encumbersome. In the end, we didn't need it. Just the IMU itself was giving us good data for attention. Because if you're not moving your head much, you tend to be focusing. And Gershon worked off of that to make it happen. So we built an experience that, usually when I put on any kind of VR gear, I'm happy, or even AR gear now, I'm happy to take it off. I wanted to keep this on because I put it on, I was enhanced. I had super hearing. It's almost like if your ears are clogged, you have them cleaned out, you hear a different world. It was like that here. And since this bone conduction wasn't covering my ears, it was adding to it. We had an IMU to track the head, so the sounds from the sensors and the microphones would naturally track where you were looking. This is Dan Gager. He's a fellow at Bose. He's designed every great headphone and earbud that they have. So for him, it's a different experience. That's a naturalist to work with. And she's talking about the spatialization, how it moves with her. You know, she's hearing things that you can't hear with an ear, but it sounds natural when we incorporate it with head motion this way. So this leads to the future, right? And this one thing I'm really interested in is what we call scalable presence. You know, we have full up immersion. We have, you know, peripheral connections like my watch to my doorbell. There's a whole space in between that's fascinating. How do we address that? It's one of the questions I'm bringing to my group. One of my students, Sam, is thinking about how to connect people to things that don't necessarily have a physical analog as well. So like an AI intent, things like that. Can you start using different sensory channels together with plasticity and how people respond to them to begin to incorporate these additional senses? You know, can you, in a drone swarm, this is a flock of birds, can you be the leader, be a follower, be the swarm? Can you move your awareness in between them? How will you do this? It's a great question, and it's leading to some interesting projects. And finally, yet another sensor net, kind of inspired by Tidmarsh. We're going to put a sensor net in the moon, I think. We didn't make this version of Lunar Outpost, but NASA got very interested in it. We're talking to a team there. Hopefully this evolves into a real manifest that we can try. The moon is much closer than it used to be. There are many missions going. There are opportunities to put things on the moon, even for our community. So we designed a sensor node you can ballistically deploy. You just launch it with a spring load. And you know, the moon's 1/6 gravity. You can go quite some distance, no atmosphere. You can calculate exactly where it's going to land and populate your nodes as you have to measure what you want and also maintain wireless connectivity. So based on a microsat, this is a microsat kind of off-the-shelf version. We made a little node. This node has got redundancy because we don't define where it's going to land. It can land on any face and still do its mission, which adds to weight. But you can do different things. I have ground penetrating radar go down with an antenna goes down, communications go up. But again, this is evolving quite a bit. It's small, it's modular. We can put different kinds of sensors into it. This is probes for looking at dielectric response, looking for water, but many other things we can do. We can trade boards in and out. This is evolving very quickly now. We'll know hopefully soon if we get on a manifest in the near future, in which case we'll accelerate this program a lot. It's exciting to think about doing a sensor network of the kind we built actually in another planet. And then we think about hybrid mission ops as well. This is using the ideas we developed in Tidmarsh. You know, we have things we're putting on the moon. We have people on Earth. Can you start to combine these assets in these virtual hybrid mission operations where you can bring people in at different levels of detail, look at AIs, manifest different things, and how do you do it? We're collaborating with David Newman, very well known in NASA work, as well as now being the new director of the Media Lab in this work. This is wayfinding for the rover that's going to the moon. This is something Don Haddad did in Unity. You can be in the rover as you do the mission planning. You can be above, some combination. So, in conclusion, I'm not exactly a pessimist. We're in complicated times. I think humanity is definitely in the midst of a transition. And I think if you think about the virtualization, it has both good and bad aspects, but it's intriguing to think about it. This is kind of the extreme end, right? The vision of the Matrix where everybody is wired into this system, and the drabby real world isn't what counts. It's more this one. It's been explored in speculative fiction a lot over the years. Eventually we may get there. People working on prosthetics and give it decades. This is a possibility. But in the meantime, we have to live with what we can wear, and it's still a lot to do. I think for me, this is part of a metaverse presentation I gave. I think it's a nice way to end. Are there ways in which you can have this virtual presence, this augmented presence, give us a fuller and richer connection to physical reality? Not remove us from reality, but plug us in better, like what we did at Tidmarsh. I think it's a fascinating approach. What are these new interfaces going to be? And again, this whole scalable immersion between being fully immersed and peripheral. Can we address that as a continuum? What is it going to be? And finally, when we have all these sensors everywhere and we're connected in different ways to them and to each other, where does self-stop and other begin? I think it's one of the poignant questions of the current time, which has positive and negative connotations. But I think in the end, there's a lot of stuff to explore, a lot to be gained if we do it the right way. So thank you very much.